Thank you so much, everybody, for being here. I know the weather is horrible, and we're about to tell you about global warming. So the irony is not lost on any of us. I'm so excited that you guys are here, and for everyone who is at home and comfortable and warm, joining us on Zoom, we're excited that you're joining us as well. I am so excited to kind of introduce our speaker and our topic for this evening. So it is Dr. Qian Lu. She is Oh, is my mic on? Can you hear me? Am I too far away?
No.
Perfect. Okay, I'm too far away. I'm so sorry. But this is Professor Qian Lu here. She's a research assistant professor in the Department of Geography and Geoinformation Science. She received her PhD right here at George Mason, so she is homegrown, which is really, really exciting. And so accomplished and wonderful that she is being poached away from us in the fall. She is going to be an assistant professor in the School of Natural Resources at the University of Missouri starting this fall, so that's a promotion and an exciting thing. She is going to be telling us about her research that's focused on air quality and climate science more broadly, and the really cool cutting edge techniques that she uses, including artificial intelligence, to kind of build the best possible models of our planet. So without further ado, I would love to introduce our speaker, and you're free to take it away.
Thank you, everyone. Thank you, Amanda. Everyone, welcome to my presentation.
Okay.
Hi everyone, welcome to my presentation. Today I'm going to talk about my research on using artificial intelligence and spatiotemporal methodologies to analyze the climate factors. And here is a little outline of my presentation today. First of all, I will briefly introduce what is climate and climate change. And after that, I will talk about my 3 aspects of research, including the climate factor analysis using AI, global temperature data generation for climate change study, and finally, I will talk about human impact on the environment. I will use my series of research on the COVID-19 impact as an example. First of all, let's talk about what is climate and climate change. Climate is a long-term pattern of weather in a particular region. And weather refers to the atmospheric condition that occur locally over a very short period of time, from minutes to hours or days. Some familiar examples can include the rainfall, the snow, the clouds, winds, floods, or thunderstorms. But climate, on the other hand, refers to the long term, usually at least 30 years. Regional or even global average of temperature, humidity, and rainfall patterns over years or decades. And climate change is the long-term shifts in temperature and other weather patterns. The climate change occurs when the incoming energy from the sun and the outgoing energy from the earth are not balanced. When they are no more equal to each other, the climate of our earth will be changed. And there are majorly 2 kinds of sources that can introduce the climate change. One is the natural sources, such as changes in the sun's activity or large volcano eruptions. These factors can change the energy that received by our earth. Another type is the anthropogenic sources. This type of sources majorly includes the human activities on burning of fossil fuels like coal, oil, or gases. These fossil fuel burning activities can emit a large amount of greenhouse gases. And the greenhouse gases in the atmosphere can trap some of the heat from going out of our Earth's atmosphere. And this trapped heat can make our Earth hotter and hotter over years. And we actually can think of our Earth as a car. And the greenhouse gases is like the windshield of the car. And the sunlight can pass through the windshield and warm up the inside of the car. But the heat cannot go outside of the car through the windshield. So the inside of the car will become hotter and hotter. And the climate scientists have shown that these human activities is the causes is responsible for virtually all of the global warming in the recent 200 years. And then we want to ask, why did climate scientists forecast the human impact? How did climate scientists forecast these human impact and severity of these climate and environmental changes? They run computer simulations based on their understanding of the physical dynamics of our climate and environment. And these computational models are climate models. Which is often refers to the general circulation models, global climate models, or GCMs. These models must include all aspects of the atmosphere, the surface, and the ocean, which all affect the Earth's energy balance. And that case, the input is, the more affected they include, the more accurate their climate model will perform. And these models can help us understand how our action can affect the future climate. And the results have shown that when the atmospheric carbon dioxide is doubled, the surface temperature will increase by 2.4 degrees, and the stratospheric temperature, on the other hand, will decrease by 10 degrees. So my first aspect of research is how to use AI to analyze these input factor of climate models to estimate them with a better accuracy and finally make these climate models perform better. And here I will use cloud fraction retrieval as an example. And cloud, we all know that cloud is one of the most common natural phenomena that we can see them almost every day. But cloud is also one of the most important climate factors that impact the energy budget of the whole Earth. And we can see from this figure, the incoming and outgoing energy from the Earth is totally different with and without the cloud. So when we use the satellite data as the input of a climate model, it is very important to know if there is cloud or not, or what is the proportion of each satellite imagery pixel is covered by the cloud, because different proportion of the cloud will have different warming or cooling effect for the climate models. So this proportion of cloud for each satellite imagery grade is called cloud fraction. It is very crucial for modeling the downward radiation from both the top of the atmosphere and on the Earth's surface. So it is the one of the most essential input of the numerical weather predictions and global climate models. However, the cloud fraction of one of the most commonly used satellite imagery infrared sounder has rarely been estimated in the existing literatures or studies. They only focus on the cloudy and clear sky delineation or effective cloud fraction simulated from radiative transfer models. And this kind of cloud fraction is not real cloud fraction. They are model simulations. And those traditional method is often includes complex data pre-processing procedure, and they often use arbitrary thresholds in their algorithms. So we want to ask the question, can we leverage the most state-of-the-art AI technologies to build an accurate and fast cloud fraction retrieval model with as simple input as we can to increase the efficiency? In order to build this kind of model, I use the two kinds of data sets. One is the cross-track infrared sounder CRIS. The CRIS has many channels, which is it has 2,211 channels, which means it has a very high spectral resolution. But its spatial resolution is kind of coarse. It is only 13.5 kilometers. And the other data set I used is the visible infrared imaging radiometers WIRS. The WIRS only have 22 channels, which means its spectral resolution is much lower than CRIS, but its spatial resolution is around 300 meters and 700 meters, which is much higher than CRIS. And these two kind of data sets, this two kind of sensor is on the same satellite platform, which called SNPP, NOAA-20, NOAA-21. These are all satellite names. And they are observing our Earth at the same time and same location, which can provide us an opportunity to both use the high spectral resolution from CRIS and high spatial resolution from WIRS. And the key to this study is to build the correct relationship between these two kind of data sets. And this figure is just the relationship of the two data sets. The figure A on the top is how a scattering line of CRIS look like on top of WIRS imagery. And figure B here is when we zoom into a set of CRIS pixels. And figure C is the co-location between these two kind of data sets. The big circle is, each of the big circles stands for one CRIS pixel. And each of the blue and green dots, the small dots, are the WIRS pixels. So the cloud fraction of each CRIS pixel can be calculated by the ratio of cloudy pixels of WIRS within this big CRIS pixel. The figure B is a cloud fraction calculation result of figure C, and figure E is the calculation result of this whole scan line. And the cloud fraction information we just calculated can be used to train the AI model. For the AI model, I used a deep neural network model. And this model contains 4 parts. The first part is the input layer. It contains all the 2000 CRIS radiances and their corresponding WIRS, corresponding cloud fraction calculated from WIRS. But we can see that the number 2000 is a large number for AI model to be trained. It will cause a lot of computational burden to train the model. So I performed a principal component analysis on the CRIS radiances and transfer the raw CRIS radiances data to a new projection. And this projection can concentrate the most useful information onto the first few principal components. Principal components here I will refer to PC. And after several rounds of sensitivity tests, I decided that when the PC number is 77, the model yield the best performance. So by using PC analysis, I reduced the input variable number from 2000 to 77. And after the PC analysis, the data will go into the second layer, the PC layer. And the third layer is 3 fully connected hidden layers. And the last layer is a output layer that yield the final cloud fraction results. And I used several use cases to evaluate my model's performance. The first set of use cases are daytime and nighttime of October 30th, 2018. This is daytime and that is nighttime. For both daytime and nighttime, the first figure on the upper left is a WIRS imagery, and the second figure, figure B, on the top right, is the real cloud fraction calculated from WIRS, and figure C is the prediction results by the model. Figure D is the difference between the truth and the prediction. We can see that the model accurately predicts most of the cloud fraction for both daytime and nighttime. But we can also see some lower accuracies over partially thin cloud areas and over high latitude. You can see that MFT over higher latitude here is much higher than that in the lower altitude, the latitude. This is because over the thin cloud region, the sensor will receive stronger surface signals. These surface signals will confuse the model and make them perform worse. And over the high latitudes, there are a lot of ice and snow, which can be confused with cloud. So the model perform worse over those kind of regions. And we can also, from this table, it is the quantitative assessment of the model. We can see that the model performs better over ocean than over land. This is because the land surface is more complex than ocean. This will make harder for the model to predict over land. This movie, This movie is the result of a continuous 10 days of use cases from June 1st to June 7th in 2020. And by doing this kind of evaluation, I can prove that my model also perform very good over a continuous period of time. Now that I have talked about the cloud model, input factors of climate models, another way to study the climate change is using observation data to detect the actual climate change. And my second current research is to generate high quality global temperature data set from satellite observations. Let's take a look first. What kind of observation data we can use to monitor or detect the global temperature? There are several. First is the surface weather station. And this kind of station is mostly distributed over land. And over ocean, we have ocean buoy stations and monitors mounted on ships. We also have weather balloons at about 25 kilometers above the surface, which can detect the near surface temperature. And we also have some active sensors like LiDAR and radar to help us monitor the temperature. However, all these surface or near surface observations are distributed very sparsely, either over land or over ocean. And they are sometimes limited under bad weather conditions. Like if there is a tornado or hurricane, the ships cannot go outside. They cannot have the temperature data on ocean. And sometimes under the war condition, the surface weather stations can no longer be operated. However, there's another kind of method that can provide continuous and global coverage of temperature, which is the satellite data, especially the satellite sounders. Because satellite sounders can go through the atmosphere and detect the temperature of different layers in the atmosphere. And the history of satellite microwave sounders operated by United States and European Space Agency can be dated back to 1979. So they have more than 50 years of data set. And we can see that in the future 20 years, the time after present, they also have plans to launch a few more satellites that carry this kind of sounder sensor. So it plays a vital role in measuring the global atmospheric temperature trends. However, although the calibration has been conducted for each individual sensor, the inconsistencies still remain between different satellites. This figure shows the temperature differences between different satellite pairs. If there is no error, different satellites, different sensors, which are monitoring the same time period, they should report exactly the same temperature value. So these temperature difference should be zero. All these curves should be around the zero line. But as we can see that in reality, this inconsistency can be as big as 0.5 K positive and negative. One of the major error sources is the diurnal sampling difference. This is because different satellites is observing the Earth at different local times. And their scanning local time is determined by their orbits. And sometimes this error also occurs when they're always tripped with satellite aging. Sometimes their battery may be deficient and their orbits may become lower, which means nearer to the Earth's surface. Let's take a look at this figure. This shows the scanning local time of different satellites over their operational time. Let's take NOAA 11 as an example. At first, it is scanning the Earth at 1:30 p.m., but after 11 years of operation, its scanning time becomes 9:30 p.m. As we all know that temperature at 1:30 p.m. and 9:30 p.m. is totally different. So if we don't calibrate these sensors or data set, these errors may cause spirit trends in the long-term observations. So this is also my current work with NOAA is to build a diurnal correction model. Generally speaking, we just take a series of satellite sensors that operated in very stable orbit that does not have any drift as an example and correct all the other sensors to this reference. And these two figures are the temperature differences before and after the diurnal correction. We can see that, and I just introduced, if there's no error, the difference should all be zero. So after our diurnal correction, these data set, the difference in these sensors data set become zeros, and they don't have any trend in their temperature difference. And using our corrected data set, we can monitor the trend of the atmospheric temperature. And in our study, we have already found a increase in global mean trend of 0.14 K per decade in troposphere during 1979 to 2021. And we can also see an even greater increasing trend after the year 2002. The trend is 0.22 K per decade. This increasing trend means a accelerating tropospheric warming. And I also did trend analysis of tropical precipitation in both space and time. In my study, I found that the total rainfall amount does not change over the past 13 years. Total rainfall amount is on the top. We can see that there's no very significant trend. But for the rainfall frequency, the second figure, we can see a very significant decreasing trend. And for rainfall density here, we can see an increase in trend. This means there are more severe precipitations in the recent years. Now that we have realized that humans are responsible for most of the climate and environmental changes in recent years, so my third aspect of research is just looking into how human activities can influence our environment. And I conducted a series of the study on spatiotemporal analysis of the impacts of COVID-19. Since the first case was reported in 2019, the COVID pandemic have influenced both our natural and social worlds in many domains, such as the policy and administration, the environment and climate, economics, human dynamics, social implication, and medical services. And among all these domains, environmental impacts often attract huge attentions from both the public and the academia. This is because the environmental factors are essential indicators of industrial production and human activities. For example, the emission amount of NO2, nitrogen dioxide, it can show how much how much industrial production we have done in this period or in this over this region. And the analysis of these environmental factors can provide a databases for our economic loss assessment and reopening. However, if we want to conduct such kind of analysis, we still have several challenges. First of all, what kind of environmental factors are influenced by COVID, and how different these factors are influenced in the COVID? So in my study, I considered several environmental factors, including nighttime light, surface air pollution, and atmospheric NO2. Second challenge and question is that, do all these factors have similar response in different regions? So I selected several regions, including China, California, and several other countries all over the world, which have totally different policies in mitigating the COVID, to see if they have similar or different methods. And thirdly, how to explain the changes of these environmental factors and isolate the impacts only from COVID-19. Because these the patterns of these factors also impact by the climatology, by the environmental regulation policies and interannual variations. And finally, what kind of data set is needed and how to combine all these different data sources together to extract useful patterns. In my study, I accept the environmental data such as satellite imagery, ground observations. I also considered various number reports, the political boundaries of different regions, the policy, mitigation policy stringency index. And I designed a workflow to conduct the analysis, including first the acquisition of original environmental data, which is usually the granular data like this. And then I integrated these original data together and produced some daily maps of different environmental factors over my study region. And then these data maps will be aggregated in both space and time. After temporal aggregation, we can get some periodical maps over the study region. And after the spatial aggregation, we can get the time series of the pandemic year and the mean of historical data sets. And after when we get these maps and time series, we can conduct difference, we can calculate the difference between before, during, and after the lockdown and compare the patterns in pandemic years with long-term climatology. And for some factors, I also conducted categories analysis to separate them into different social sectors, like residential, public facilities, or commercial centers. And finally, I visualized and interpreted these patterns in combination with the location of emission sources like the power plant, the various number reports, policy indices, and industrial productions to explain why we get these kind of patterns. My first study of this series is the impact of COVID-19 on air quality and nighttime light in China. And these two figures, this figure is the nighttime light changes in provinces of China, and that one is the changes of air pollutions. Through my study, I found that the air quality become better and the nighttime light become weaker during the lockdown period. And then like I said in my last slide, I categorized the nighttime light into 3 social sectors: residential area, the transportation and public facilities, and commercial centers. We can see from this histogram, the residential areas have a much stronger nighttime light than before during the lockdown. And transportation and public facilities, the nighttime light there does not change that much. And over the commercial centers, the nighttime light become much dimmer than before. The reason I think is obvious because during the lockdown, we need to stay at home. We cannot go outside to shopping. So the commercial center becomes dimmer and the residential areas become brighter. But for those transportation, the roads, the highways, the like public facility like hospitals, they are still in use for saving life or transport some essential goods, something like that. So they did not change that much. And I also specifically looked into the city of Wuhan, where the first case was reported. Figure A is nighttime light before the lockdown, and B on the right is the nighttime light during the lockdown. And C, the figure below, is the difference between these 2 figures. So we can see that these 2 areas in circle, these are 2 big commercial centers in Wuhan, and they become dimmer here. And these areas are some popular residential areas. They become much brighter than before. I also look into the air pollution in California. I analyzed a time series of different air pollutants, including the ozone, PM2.5 top right. This one is PM10. This one is NO2. This one is CO. We can see that the blue curves is the time series of the pandemic year, and the red curve is the mean of 10 years, the historical 10 years data. We can see that before the lockdown, roughly before the end of February here, the 2 time series is comparable to each other, they're similar. But after the lockdown, we can see that the blue curve is much lower than the red curve, which means the emission of air pollutants is much lower during the pandemic lockdown than the same period before. Those maps are the changes of atmospheric NO2 over California. we can just take a look at this figure. These are this figure is the difference between lockdown and before lockdown. This area is concentrated by power plants. You can see that the power plant area become the emission over that area become much lower than before, and residential big cities over C and B, the emission becomes stronger. This is because people kind of stay at home, and the industrial production is stopped during the lockdown. And then focused on several different countries over the world, including the United States, Brazil, UK, South Africa, China, and India. And the conclusions is similar than my previous study. The NO2 of most target countries is significantly decreased during the lockdown. But the United States during the lockdown is actually increased by slightly 1%. We can consider that the emission of United States during the lockdown is similar with before. We don't have any emission change in NO2. And after the opening, the NO2 rebounded in most of the target countries. And I think that's all for my current study. And thank you for taking time to attend my presentation. And if you have any question, I'm very happy to answer. Thank you.
Thank you.
You got what you in? I'll start. Thank you so much for your talk. I had a quick question about the middle scenario that you were presenting with the satellite data. And I just want to make sure I'm understanding the question, because what it looks like to me is that the discrepancy between the satellites, different countries, that difference is actually bigger than the overall change once you normalize the data, right? And so what I'm thinking is that kind of, it's not just like you're making the data a little bit more perfect with your kind of methodology, the data is almost unusable, right? Without the things that you guys are doing to correct that. So I guess I just wanted to hear a little bit more about how important it is to make these corrections correctly and make sure the data is how quality as possible. Because from what I see, if you don't do that, the data is unusable, right? Yeah. It's not even just like a little bit. You know, so I'm wondering if you come more.
Yeah, if we don't, this study, right? Yeah, if we don't track the data, as I said, when the two satellites is observing the Earth at the same time, same location, the temperature they see should be exactly the same. So the difference should around 0 lines. But we don't correct them, because as we can see from this figure, each satellite just cover a short period of time. Each satellite cannot cover this whole time. We need to combine them together. Yeah, if we want to combine them together, we must make them comparable to each other. If they contain such big difference, if we just combine them directly, there will be very big errors. And the temperature trend we detected from this arrow data, we cannot trust it. With this kind of data, maybe the global warming would be like much more or even much less. We are not sure. We should make the data correct, and then the trend being detected is correct, is trusted.
Yeah, that's fascinating. I didn't realize how.
Yeah, the raw data contains a lot of errors. Diurnal correction is just one of them. We also did a lot of different other calibrations. Yeah, each of the calibration may cause a scientist lifetime to develop, to create the algorithm, to make the algorithm perfect. We do have those kind of scientists in NOAA, just to focus on one algorithm their whole life. Yeah.
You have the microphone.
That was fascinating about the clouds. Over the past, let's say, 50 years, have the type of clouds and the amount of cloud cover Obviously, there's all different kinds of clouds and then different densities and probably different ways they trap heat. What is the overall picture of clouds over the past 50 years? If we look over the world, does that track in any way with the global warming or global change in terms of your and then how do you predict that going forward into the future?
Okay,
Does it make any difference to see the clouds or try to affect the clouds? And some people have said if we could change the cloud cover, we'll solve the climate problem. Tell us more about clouds.
yeah, the cloud actually, right, this is a true color imagery of satellites that of our Earth. We can see that like most of the area is covered by like cloud, like those white regions. And as I introduced with and without the cloud, the structure of incoming and outgoing energy of the Earth is totally different. So of course, the cloud is very important to our climate modeling or climate change study. Actually, my home study is not yet reached to the analysis of cloud coverage over long term, cloud type statistics over a long period of time. My own study haven't yet.
What do you think? What do you think? What do you think is the clouds and do clouds offer some way for us to alter the climate in the future or make a difference?
You mean if the cloud coverage or cloud type will change in the future? I think if the global is keep warming, I think it will be changed. Like my study of telescope precipitation, we have detected much more severe precipitation in most recent years. And severe precipitation is produced by different clouds than those lighter rainfall. If we have more severe precipitation, which means we have more type of cloud that produce those thunderstorms like tornadoes and like hurricanes like that. So I think since we know that the precipitation type is changing, so I think the cloud type is changing due to the global warming.
So as we have more global warming, we have more precipitation.
Precipitation amount actually did not change that much, a slight increase. Yeah, but the rainfall density is increasing very significantly, which means we may have less rainfall event. For example, we may have a 10 precipitation in our region in the past in last year, but this year we only have 5 precipitation events, 5 days of rainfall. But this 5 days of rainfall is much harder than those precipitations in last year.
Does that affect dryness or drought or or farming because the rain is
concentrated in very short period, and in other period, there will be no precipitation and drought will come. And during the precipitation days, flood will come.
But we can, even with this limited beginning part analysis that you have, we can see some trends that we might use in thinking about the future, what we could do.
Yeah.
How we store the rainfall over a shorter period of time, maybe for later irrigation uses.
Yeah.
I just wanted to ask about the persistent layers. Those are you said you measure the cloud fraction using them.
Yes, let's take a look at this figure. The crate has a very big footprint. The crate, the crate pixel is much smaller, as you can see that compared to the crease, the weird's pixel is only some sort of small dots. So, when you know the cloud condition, the cloud information of weirs, we can know that which pixel of weirs is cloudy, which pixel is clear sky. Then we can calculate the cloud fraction of a weir's big footprint using the weirs data. I know this name of satellite sensors is very confused to you if you're not in this domain. So,
And then,
yeah,
what kind of information do you gain from measuring like the cloud pixel, like the density of the clouds or?
just cloud fraction, the proportion of big crisp footprints, how much part is covered by cloud? Like 90% of the pixel is covered by the cloud, or 50% of the big pixel is covered by clouds.
How do you interpret this data? Like, how do you apply it? For example, like in weather forecasting, or what kind of?
My task is calculating the cloud fraction using AI. When I get the result, I can hand it to the climate modeler. They will use my result as an input to build their climate models. The better result I get, the better accuracy they can get for their climate models.
And these are satellites, this model, that I didn't
Yeah, these two data are satellite data sets.
So how do you launch them? Do you like, are they already in the space?
By rocket.
Really?
Uh-huh.
I never knew that.
So these are just a few of many satellites you could be getting data from, is that right?
Yes, yes. I'm working with a lot of satellite data sets. All these my studies have been using different data sets. Yeah.
What about the height of the clouds? Is the height and density, you probably don't look at that, but does that affect, do we understand how that affects the heat in the atmosphere? Whether there's, I think, high clouds, low clouds? You probably can't measure that with your system, you're just looking whether it's blocking the earth or not.
Yeah, my study, I do not focus on the cloud height, cloud top height or cloud base height. But satellite imageries have those kind of products. They have products for cloud top height and cloud base height. And when we calculate their difference, the difference would be the cloud height.
And would you calculate, when you think about warming, does that make a big difference in terms of how close the cloud is to the earth? Does that track the heat in a different way?
I think if there's no greenhouse gases, the cloud will not change the Earth's climate. The greenhouse gases change the climate of the Earth.
But if there's a certain kind of cloud that's over the earth, and that part of the earth is not going to be heated by the sun as much, right? It'll be in shadow. So that you can imagine that the cloud cover would contribute to the heating below, don't you think?
Yes, different clouds will have different warming or cooling effect for our Earth. But in general, when we consider the whole globe, the total energy should be balanced without, if you don't have any greenhouse gases effect, the cloud, the whole global cloud will, the energy would be balanced in common outgoing the Earth. Yeah, the cloud will not influence our climate, will not change our climate.
The first question, back on slide 5, you had a bullet that indicated that there was a cause for surface warming at about 2 degrees Celsius, but that the troposphere dropped 10 degrees. Can you please explain how that operates? I don't understand that mechanism.
This is because the greenhouse gases is usually in the troposphere level. So it traps the heat in the troposphere and in the troposphere and our surface. So the heat cannot go outside, right? The outside is the stratosphere. So the heat cannot go outside of troposphere. So the stratosphere will receive light heat. So it will become cooler.
And then one more question, please. The neural network that you use, I'm not at all familiar with. I'm making an assumption that that was a very hard part to study to build that network and to test it, or to build that model.
Model, actually, I use Python to write all my codes. So the Python has packages and models that I can directly use. I don't need to develop the DN model. The DN model is developed by those computer scientists.
Okay,
So I just use it.
thank you.
Where do you plan to go with your work in, let's say, 5 to 10 years in the future? What are your future plans and big challenges that you're gonna go after in your new job?
Yeah, my new position is focusing on climate science. And for my study, firstly, I will conduct analysis on other climate factors. Now I'm focusing on clouds. I may, more specifically, cloud fractions. I may focus on cloud heights, like you just mentioned, cloud top heights. All these factors I can focus on. I also can focus on retrieve the air pollution concentrations, like retrieve the precipitation densities, precipitation rates. I can do this. There are a lot of climate factors that I can focus on. And also, my work with, hopefully I can continue my work with NOAA. I hope they can continue to fund me. So for my other parts, I will continue to, because, you know, our version of data is only to, I think, 2022, and there will be future sensors launched in the next 20 years. I will keep on doing this to include more sensors. Because when you include new sensor, you should recalculate all these factors, all these numbers. You need to renew that, recalculate that. So my future work is also update our algorithm. Yeah, with new
Does
sensors.
NOAA have their own satellites? Or do they just use NASA satellites? Or
I
do
think
they
all these
design
satellites.
own satellites specifically for weather and then shoot them up?
Like I mentioned, they have NOAA 20, NOAA 21. I think.
Those are NOAA designed satellites, right?
Uh,
Specifically for that, for the weather purpose.
Design satellite, I think they don't. My department is only working on processing the satellite data to calibrate them, to generate them, to use them, something like that. For satellite designing, I think they are belonging to NASA or something.
They're getting some of your data to help them form the next generation of satellites, what they make the satellites do, or how they make sensors better,
Yeah,
because of what your
yeah.
data shows. Right?
Yes,
Potential.
the sensors, yes. Maybe our data may give them some suggestion that you need to improve this way. They have some arrows here. Maybe you can correct them, something like this, maybe.
As a real climate scientist, what hope can you give us for the future? And can you give us any suggestions or ways to look at the climate change as a public, as citizens, so that we will worry less, or something that we can do more, so that we don't feel as helpless about this problem? I know it's a big question, but
Yeah.
relying on climate scientists like you to give us some good hope.
Good question. Thank you. For my work, I'm providing data, I'm providing analysis results. So my work can show people if the climate change is real or not. If we make our data more perfect, we can show you that, we can confidently show you that there are climate changes. Or if with our work, the trend, the increasing trend of temperature becomes lower, we will tell you that, oh, our Earth's condition become better. We have done something because we have done something, maybe shut down some industrial power plants. We have do something to make our Earth better. So using my data, I can show people that with all of your effort, our Earth become better. So I think these are our climate scientist contribution to the climate, to tell people if the climate change is real happening over there, because maybe some of the people still do not believe it, or they think, or some people will think the condition is very severe, and maybe our Earth is exploding in a few years. But with our data set, we can give them scientific proof to tell them the truth. Yeah.
Your data only goes up to 2022, I thought, when you were
Yeah.
telling it. And that's before the pandemic. A lot of the pandemic, right? A lot of the pandemic effects. So the question is, I mean, 22 is pretty much certainly the last end of the pandemic, right? But do you think that looking back on it in a couple of years, you'll be able to see that when we were in the pandemic and less people were driving cars and there was less people were flying airplanes, and so there was less CO2 potentially from all those differences in population behavior around the world, that we could see a corresponding difference at that period of time related to human behavior in the pandemic. Is that a realistic thought?
Yeah, I think use our satellite data, we can show if the pandemic change our climate or not. But the pandemic period is from 2020 to 2021. In 2022, many of our cities is.
Yes, so if you look back on that, can you see, when now compared to now?
Maybe.
Can you see something that gives proves to the world that changing our behavior makes a difference?
I think so.
In terms of,
At least those air pollution, we can directly see the difference, like, by research for the impact of COVID-19, we can directly see that over those periods, the air pollution decreased very significant. Yeah, but for long-term climate, we need more time to say. Maybe the pandemic period is not long enough to affect the climate. Yeah, the pandemic year only at most 2 to 3 years. Maybe this period is not long enough to influence the whole climate.
but it did show from your studies that there might be some evidence of human activity changing during COVID.
Yeah, that's good.
Made a difference or changed some of your measurements. So that shows a skeptic that human behavior has an impact on the climate.
Yeah, yes. Different. Yeah, from the satellite, we do see a lot of change due to the pandemic policies. Yeah.
So how do satellites get calibrated? Do they get calibrated in space, or do you recall them and then?
I think both. They get calibrated in many steps. Some people is doing on satellite calibration. Some people is doing calibration for level 1 data, level 2 data, level 3 data. And For example, our team, we probably conducted 2 or 3 different, just within our small group, 2 or 3 different kind of calibration, lab kind of calibration. Maybe you may not understand, but I can tell you that, the data, used, that can be published to the public is, have been going through a lot of calibration steps.
Well, I think we're done for the evening. If you have any other questions, you want to speak to our speaker directly, feel free to do that. But, thank you so much for braving the weather.
Here's my email. I don't have any questions.
I think that.
Thank you for all this help and all the next. Thank you for coming here.